So I think we are clear so far. In the last class, we have discussed about the properties of charges, the basic kinds of charges, what is the SI unit of charge, and then this is where we have arrived at. And then we have taken up this question: how many charge carriers are equivalent to 1 coulomb of charge? If you would have carefully worked out the basic mathematics, we arrive at the conclusion that 6.25 into 10 to the power of 18 electrons put together would constitute 1 coulomb of charge. And the method is already discussed with you. 1.6 into 10 to the power of minus 19 coulombs will be for 1 electron. 1 coulomb for how many electrons? So this basic unitary method in mathematics, when we use, we finally arrive at the conclusion that 6.25 into 10 to the power of 18 electrons are there in every coulomb of charge. So with this we move to the next module, electric current. Before we go to electric current, let's see what is water current. So whenever there is a water stream that is flowing, the other name for the water stream is water current. We have one side still water, for example in the check dams, and then the moment gates are opened up, we see water flows. So flowing water is called water current. Similarly, moving charges or flowing charges is called electric current. Movement of electrons is called electric current. So electrons are the basic charge carriers in our circuits, and then whenever these electrons are moving in any circuit, we say that there is electric current. So mathematically we can define this as the amount of charge flowing through a particular area in unit time. So whenever we define this physical parameter of electric current, this is how we define it: the amount of charge flowing through a particular area in unit time. The same thing when we keep it in an equation form, it comes this way: capital I is equal to capital Q by T. Capital I denotes the electric current, capital Q denotes the total number of charges that are moving, the total number of electrons that are moving, and T denotes, small t denotes the time. So this is how we express capital I is equal to Q by T. And then what is the SI unit of current? We state it as ampere. So ampere is the SI unit of current. We all are aware of the SI unit of length is meters, mass is kilograms. Similarly, the SI unit of current is ampere, which means current is basically measured in amperes. So how is it measured? So we have this particular instrument called ammeter. So in most of the science laboratories we find this instrument. It is called the ammeter. So in the basic electric circuits we use this to find out how much current is flowing in a particular given time. So this is one kind of instrument. Suppose we want to make a more sophisticated measurement, we want to be more accurate and precise, then we use this particular thing called multimeter. The difference of these two is very simple. I think you understand now. Ammeter is the analog equivalent to multimeter, which means when you make a measurement with the ammeter, it gives an analog value. If you want digital value, more sophisticated, more accurate, precise to the point, then we use this multimeter. It's like your analog watch. It shows the basics of measurement of time. We have the hours hand, minutes and seconds hand, that's all. But if you want to be more precise and then know what is the milliseconds and those further things, then we go for a digital one. So basically these two are one and the same, but this is the more latest way or the most accurate way of measurement. Okay, let's have a look at this picture. This clearly shows us how electric current flows in any given circuit. Let's take an example. All of us are aware of what this is. I've got a charger, a mobile charger, and then there is a USB cable here, and then this is connected to the adapter. Now, if I take this pin and connect it to my mobile, definitely we all are aware of the fact that the mobile would not be charged. Does it mean that there are no electrons in this wire? Yes, of course, in every object electrons are there, but there is no electric current in this. So what should I do to make this allow the flow of electric current? The moment I connect this adapter to a socket, then we know that current flows from the socket through the wire to the mobile. So therefore, the electric current has to flow through the wire so that the electrons move and then they charge the device. So now it's very clear that though electrons are there, there is some external force that we need to move these electrons so that they move and then complete the electrical circuit. Let's see what it is. We come to the next module called voltage, or it's also called the potential difference. Before we discuss anything related to this, just observe these pictures. We have flowing water here. We have a ball which is held at a particular height. Don't bother about any other things, just see the ball is at a particular height, and then the moment you leave, it falls on the ground. And then we arrive at this. So let's see what these pictures try to tell us. Suppose we store water and then we want to make it flow. We know that there is a certain height difference we need. The water that is stored in a dam, it is very still unless the gates of the dam are opened. Once the gates are opened, what do we observe? The water which is stored at a particular height, it starts flowing from that particular height to a lower height or a point which is at a lower height. So therefore, there are two different heights now. Water flows from the top to the bottom point, and this lift allows the water to flow. Suppose there is no height difference, we say that water is at the equal level. Do we see it to flow? Definitely not. Similarly, let's take this example. The ball is there, it is placed on the ground, or say it is placed on a table which is placed on the ground. The ball is still there, but the moment you want to make it flow or you want to make it fall down, what we do, we just give a small tap to the ball. So therefore, the height difference makes the ball to move from that particular height h to the point on the ground. So if there is no height difference, the ball will remain same. Similarly, in our electrical circuits, we need to have a wire, and then the electrons in the wire are still there, they are not moving. So once we apply an external force or an external difference, what happens? The electrons start to move. So this process of creating difference is called the potential difference, which means between 2 points we create a certain height or a certain pressure difference so that the electrons move. If we don't create that pressure difference or the height difference, for example, the electrons remain same, they never move. But by making one side up and the other side down, or one side a higher pressure difference and the other side a lower pressure difference, the electrons can now find a way to flow. And then this is achieved by an object called a battery or an electrical cell. All of us, we know the moment we take a normal wire and connect it to a bulb, it doesn't glow. But the other ends of the wire, when you connect to a battery, we say that the bulb is glowing. Why? The battery makes the electrons move with a particular energy, and this is what it is showing here. The battery is connected, the bulb is glowing. If the battery is removed, all of us are aware that the bulb will never glow. So what happens now? Inside the battery, there are some chemical reactions that are happening. And the moment we connect a battery, insert the battery in a circuit, the chemical energy is being transported by the electrons, and then it is converted to the electrical energy. So electrons, a very minute part of the energy they take to move, and as the electrons move, they carry this energy and give it to the appliances that are connected. So now for the current to flow, we know the factor, we know the reason, which is the voltage or potential difference. Unless there is some difference, the flow will not happen. Unless there is some difference, the water never flows. Unless there is some difference, the ball will never come down. Similarly, unless there is some difference, what we call the voltage, the electrons refuse to move, and this voltage does the magic of moving the electrons, and then the moving electrons, we call it electric current. So let's see. So this is another analogy that we have here. Voltage is like the pressure that we apply, how much pressure we apply to the water hose, and current is the size of the hose, how much water flows. So how much water flows is the water current, and what moves the water, what pressure difference moves the water is similar to voltage. So let's go to the next slide. The difference of potential we maintain to make the electrons move is called the voltage or the potential difference. To define it correctly, this is how we say the electric potential difference between 2 points in an electric circuit is the work done to move a unit charge from one point to another point. So the 2 points that we defined are the plus and the minus, or the high potential and the low potential. If you have a look at the battery closely, one side there is a plus sign that is written, the other side there is a minus sign. So plus is the higher potential and minus is the lower potential, and now between these two potentials we see that the electrons move. So formula wise we have capital V, which denotes the voltage or the potential difference, is equal to work done, how much work is being done to move a set of charges. Okay, the SI unit of voltage is V. So if you take a battery, it is written 9 volts battery, which means 9 joules, the SI unit of work done is joules, the SI unit of charge is coulombs. The voltage of 9 volts means that 9 joules of energy is being given to every coulomb of charge that is moving. So every coulomb of charge means a set of 6.25 into 10 to the power of 18 electrons. So every set of these electrons is being given with 9 joules of energy. And then the energy lasts long as the battery is charged. The moment battery is drained, there is no more energy supply to the electrons to flow. So a 9 volt battery means 9 joules of energy is being shared or is being given to every coulomb of charge. So these set of electrons, as you have seen in the previous slide, they take the charge, they take this energy. So those charges carry the energy and then give it to the equipment to function. So chemical energy to electrical energy. Suppose you want to use electrical energy to heat energy, we can do that, and various forms of energy are being possible. So one form of energy is being converted to another form of energy. The SI unit of voltage or potential difference is volt, denoted by capital V, and then it is measured using this particular instrument called voltmeter. Like how we measure the current with ammeter, we have this particular instrument in the laboratory to measure the amount of voltage between any 2 points in the circuit. If you want to make a precise measurement, we have this particular instrument called multimeter. So multimeter measures current, it measures the voltage, it measures resistance, it measures temperature in the circuit and many more. So by turning the knob, what we want to measure, we can measure the current as well as the voltage. So if you want a more precise and correct value, we go for this. If we want a basic normal value reading for the record purpose, we can go for this. So again, the difference between those two is the difference between an analog watch and a digital watch. So this completes our understanding of this particular parameter called voltage. And then again we have this particular example, water flows. So the moment you have something rise to a greater height, it carries more energy. As simple as this, a person jumps from first floor and a person jumps from the 10th floor, we know what impact it makes. So the energy, the impact that the person who jumps from the 10th floor is because of the greater height. So the more height we increase, there is more potential which we create and then more energy. So all these things are directly related, the direct proportions they are. So the more height gives a more potential difference, a smaller height gives a smaller potential difference and hence a smaller impact of energy. Now further continuing, once we understood the definitions of the parameters like voltage and current, we also need to know the way in which their SI units are defined. For example, how do you define 1 ampere of current? How do we define this? So 1 ampere of current means the formula for current I is Q by T. The SI unit of current is ampere. The SI unit of Q charge is coulomb and then the SI unit of time is second. So when we say 1 ampere of current, we say that 1 coulomb of charge flows per 1 second, we say that the current generated is 1 ampere. The answer is here. 1 ampere is equal to 1 coulomb per second, which means 1 ampere is constituted by the flow of 1 coulomb of charge in a second. So therefore this is how we define the SI unit of current. So there are two definitions now. First thing, what is electric current? The second one, what is 1 ampere of current? Similarly, how do you define 1 volt of potential difference? We have defined what is voltage or potential difference. Now we have to define the SI unit also. How do you define 1 volt of potential difference? We have the formula V, the volt is equal to W by Q. The SI unit of voltage is volt, work done is joules, Q, the charge is coulomb. So let's see how the definition goes. 1 volt is the potential difference between 2 points in a current carrying conductor when 1 joule of work is done to move a charge of 1 coulomb from one point to another point. So 2 points are there. So for every coulomb of charge to move from here to the lower point. So let's see this. There is a charge of coulomb, a coulomb of charge here, which means set of electrons are there. So 1 coulomb of charge, if you want to make it to flow from this point to the lower point, if you are spending 1 joule, so for moving every coulomb, if we use 1 joule of energy, we say that the potential difference is 1 volt. Coming to module 4, electric circuits and symbols. Day to day we have got many appliances of how we use them, how we draw electricity and then how they convert from electrical energy to another form of energy. But the moment we want to keep it on the paper, there are set of electrical circuit symbols that are there. So let's see what is an electrical circuit mean. A continuous and closed path of an electric current is called electric circuit, which means if you are having joint of wires, if many wires are joined in such a way that they take energy from the battery and then they start distributing to various electrical components that are connected. So battery is a very earlier version of this, Let's see, now we have to get used to more source of power or potential difference, which we talk of the electrical socket. So the socket that we have, there are many wires that are pulled. So from the same socket we have certain amount of energy going to the fan, to the bulb, to the projector, tube light, everything. So a continuous closed path, if anywhere there is a breakage in the circuit, which means between those 2 points the current is not flowing. As long as the wire is straight and not broken, it can transmit current. But the moment I break this into 2 parts, the moment there is a breakage in the circuit, the current will never flow from one point to the next point. So for the current to flow and complete a circuit, we define that a continuous and a closed path of an electric current is called electrical circuit. And these are the circuit symbols that we use to denote each and every component. So the basic circuit symbols have been listed here. An electrical cell is denoted like this. So a bigger line and a shorter line. So one side plus and minus. Now we know what plus and minus is, the higher potential and the lower potential. A series of cells, if they are connected end to end, we call it a battery. If the plug key or switch is open, which means there is no flow of current, it will be like this. The moment the switch is closed, which means it is allowing the current to flow. So when we put on the switch, this is how we need to keep the symbol. The moment switch is open, which means you have put off the switch, this is how we show a wire joint, a dot here. There are 2 dots now like this. Here you have a dot, which means those two wires are joined. If the wires are crossing over, which means there is no joint but one wire is there, above the wire another wire is going, we denote it like this. Electrical bulb is denoted like this. Electrical resistance, which we would be talking of in the next lecture, would be denoted like this. A variable resistance, which again will be taking up in the next lecture, would be denoted like this or like this. Ammeter is denoted like this. Ammeter looks the way it was shown in the earlier slides, but if you want to denote an ammeter in the circuit, we have to draw it like this. Voltmeter should be drawn like this in the circuit. So with this, we would like to complete the understanding of the first 4 modules, where we spoke of charges and then current, voltage and then electrical circuits. In the next lecture, we would be discussing of a parameter called electrical resistance and Ohm's law, and then further. Sai Ram.